Consider the series, the sum from n equals 2 to infinity of 1 over n to the p times the ln of n, where p is greater than or equal to 0. Okay, I am considering it. A. Show that the series converges for p greater than 1. My gut reaction, this is probably right, maybe it won't be, and if it's not right, obviously I'm going to erase the video and never admit to any human being that I made a mistake, because I am infallible. My gut reaction is that this is a p-series. Well, obviously it's not p-series, but maybe I'm supposed to compare it to a p-series. It looks very p-series-like. Maybe I'm supposed to do direct or indirect, indirect. Maybe I'm supposed to do direct comparison or limit comparison tests. This looks like a p-series, especially when they talk about p greater than 1. That makes me think about the fact that the sum from n equals 2 to infinity of 1 over n to the p, this converges for p greater than 1 by p-series. This is the whole idea of p-series. My rule for knowing when it converges or not. If p is greater than 1, it will converge by p-series. So, if I can find some way to compare my given one to this, I'll be able to prove that my given one converges, or possibly diverges. But if I'm going to do a comparison, I'm going to have to prove that it either converges or I'll be inconclusive. I'm going to do a direct comparison because I'm thinking that the difference between this one that I know about and the one that I'm given is that I'm dividing by an ln, by a natural log of n to get this given one. So if I'm dividing, it should make it even smaller. In other words, that my given one since I'm dividing by something, it should end up being less than 1 over n to the p for all. I would write for all n greater than or equal to 2, which is the n's that I have in this problem, but you're too smart for that. Really, I need to be writing for all n greater than or equal to 3. Why am I writing that? I'm writing that because if n's 2, ln of 2, that's going to be a fraction, actually, because natural log of 2, that means log base e of 2, e is a little bit bigger than 2. Ln of 2 is going to end up a fraction. If I divide by a fraction, it's actually going to end up bigger on this side, because if I divide by a fraction, it never gets bigger. So, that's okay, though. The fact that this is only true for n greater than or equal to 3, we're still able to do direct comparison. We're still able to do direct comparison because it still happens for infinite number of n's, where it's all of the n's except just at the beginning. If it's all the n's except just at the beginning, that's okay. Or just the first few, that'd be okay. The reason it's okay is because I could make this sum into, if I plug in 2, I get 1 over 2 to the p, ln of 2, plus the rest of the sum, plus 3 up to infinity of 1 over n to the p, ln of n. And this I can prove converges with direct comparison test. This is going to be all true. If direct comparison test is going to let me prove this converges, so then this part that I'm adding on is just a number that I add to something that converges, and that'll be okay. Hopefully that makes sense. So we're kind of returning to proving this direct comparison thing, is that because the one I want to know about is always less than something that I do know converges, less than convergent means I'm still going to converge. Plus they're both positive. Remember that I need to have positives in addition to the less than. So my line I'll probably write is that because sum from n equals 2 to infinity of 1 over n to the p converges for p greater than 1, because this one I know about converges, and the given one is less than 1 over NP for all n greater than 3. Because this known one converges and the given one is less than the known one, then I conclude that the given one converges by direct comparison test. Hopefully that made sense. That was a little bit tricky that we had to forget about the fact that 2 didn't necessarily work for direct comparison and just think about 3 onward. Part B, that I've written over. Part B says determine whether the series converges or diverges for p equals 1. Show your analysis. So for p equals 1, what this is going to look like is p equals 1 means they're asking about the series sum from n equals 2 to infinity, 1 over n to the p, p's 1, so it's just going to be n, ln of n. Oh, how are we going to show if that converges? Direct comparison doesn't seem like a good idea, because if I do direct comparison, or maybe, but certainly not direct comparison to 1 over n, this is going to be smaller than 1 over n, but 1 over n diverges. Less than diverges leaves you somewhere between 0 and infinity, so who knows? Maybe I'll go down my whole list, nth term test, and it's going to pass that. This is going to approach, then an is going to approach 0, so that's fine. I could try a limit comparison, but that's not going to work. If I try comparing it to 1 over n, I'm going to have some trouble. I think the only option I have, as much as it's a last resort, is integral test. And one hint that integral test works is when I look at that, I think, oh, I can integrate that. Because I see a 1 over n, I see an ln of n, those seem like they go together with a u substitution. So, ready for this? We have to make sure that it is, what did we say, pretty darn cute? Was that what we said? Positive. Well, yeah. 1 over n ln of n is a positive number. 1 over positive times positive, it's going to be positive. So, that's good news. Decreasing, well, 1 divided by n is going to go up. ln of n is going to go up. 1 divided by something going up, that's going to be decreasing. So, good news there. And continuous, the only thing that's going to make this discontinuous is if we divide by 0, or in an ln, you can't have anything less than or equal to 0, but that's okay. We're starting at 2. That's going to be continuous. So, integral tests. You'll do the integral from, yeah, I know what you're asking. You're sitting there, you're going, I wonder if Mr. Noakes is going to go from 1 to infinity or 2 to infinity. It doesn't really matter. I'm going to go 2 to infinity. Because my n started 2, so I'm going to go 2 to infinity. Of 1, oh, because if I start at 1, I'm not going to necessarily be positive, right? Because we talked about, yeah. No, I will be positive. No, I'm going to start at 2. I'm going to integrate 1 over the function, x, ln of x, dx. And I think, oh, I don't know that one off the top of my head. Maybe I'll try some u substitution. I'll try u equals ln of x. Maybe I'll try u equals x, but that's a stupid substitution. It's just going to change the problem into u's instead of x's, and it'll still be the same problem. I'll try u equals ln of x, and I'll get that du is 1 over x dx. Oh, that's lovely, because then that turns this into integral of 1 over x dx. That's all just du. Which is 1 over u. My bounds change. When x is 2, u is ln of 2. When x is infinity, u is infinity. Or maybe I keep it with, I do an indefinite integral, get it in terms of u, change it back to x's, then use the same x's, whatever. This is going to be 1 over u is going to turn into ln of u. And I'm evaluating it between u equals ln of 2 and u equals infinity. So I get ln of infinity minus ln of ln of 2. Well, that's infinity. Because the integral diverges, the series will diverge by integral test. So, because integral from 2 to infinity of 1 over x ln of x dx diverges, we conclude that the sum that inspired that integral, 1 over n ln of n, well, that's messy, also diverges by integral test. And maybe I need to throw in there these things. I should tell the grader, hey, I did check these things. So maybe I'll say, because this integral diverges and 1 over x ln of x decreases the whole time, and it never goes back. So it decreases monotonically. And ln of x decreases because the integral diverges and that function decreases monotonically to 0. Then that summation diverges. That wasn't my best justification, but you'll look at what the solutions say. Third thing, show that the series diverges when p is between 0 and 1. This is the hardest part about this problem. That's a hard one here. I'm just going to do a nice big line, make it clear what I'm doing. I'll even switch colors just to really get myself in part C mode. Show that the series diverges for that. So I'm just going to write the series again, just so that we have it fresh to look at. Plus I'm procrastinating. 1 over n to the p ln of n. And this time we're saying that p is some fraction. Between 0 is less than or equal to p is less than 1. P is between 0 and 1. Well, that means that when I do n to the p, n to a fractional power is going to be smaller than just n. You know, what I'm saying here is that because on these p values, n to the p is actually going to be less than n, which means that 1 over n to the p ln of n is actually going to have a smaller denominator, so it's going to end up a bigger fraction than 1 over n ln of n. And that's useful, because in part B, we proved that the sum of this diverges. So if we're talking about the sum of 1 over n to the p ln of n, well, that must diverge too. Because if this diverges, and this is even bigger than divergent, means you're super divergent. That should be either a superhero name or like a diss. Like you go up to someone, oh, your mama, she is super divergent, she's so fat. So that's going to diverge. I have 45 seconds to write my justification before this video cuts me off. Let's see if I can do it. I'm going to say that the sum from n equals 2 to infinity of 1 over n ln of n diverges, and 1 over n to the p ln of n is greater than 1 over n ln of n, or 0 less than or equal to p. Oh, I'm running out of time. You know where I'm going with this. I don't want to make a new video. Direct comparison test.